evening and welcome to the September AstroTalk. Tonight I'm coming to you live from Starview Farm, the AC's new dark sky site out in central Victoria. Been up here working for a while, building these observatories, one of which I'm sitting in tonight. It's nice and toasty in here, which is good. This month we'll hear from Dr. Jacob Crossett, and he'll be talking about jellyfish galaxies. Following Jacob's talk, our very own Bill Stent, the telescope Gent, will share with you what's in the sky for late September and early October. A little bit of housekeeping. The 20th of September, on the 20th of September, we have the Galactic Centre Star Party at the Leo Mau Dark Sky Site for ASV members. And a week later, on the weekend of 26th and 27th of September, we have the Sea Lake Astrofest, so be sure to grab your tickets. Now, the Astrofest is for the public as well as ASV members. Now, speaking of Dr. Jacob Crossett, he's an astronomer and researcher who studies how galaxies transform, including searching for rare jellyfish galaxies. He completed his PhD in astrophysics at Monash University and has since worked in the UK, Chile, using some of the world's largest telescopes to study these unique objects, including the VLT and Magellan. Jacob is also passionate about sharing his love of space through public talks, telescope evenings, and citizen science projects. And in tonight's talk, AstroTalk, Dr. Jacob Crossett will discuss understanding the evolution of galaxies in dense environments and the search for jellyfish galaxies. Jacob, welcome.
Thanks. Thank you for having me, and thanks for the opportunity to share my love and passion for jellyfish galaxies and all things extragalactic astronomy and astrophysics.
They're very cool galaxies. I remember your talk down at Vastrock, and it was one of my favourites for the day. So it's part of the reason I wanted to get you on so that you could share it with everybody else, because it is quite an interesting topic.
Yeah.
So
no,
what I'll do, sorry, Jake, I was going to say what I'll do is I'm going to hand it over to you to give your talk.
Alrighty, I'll get started. So I assume my audio is all good and you can see and hear everything I've set up okay?
Yeah, everything's working beautifully.
Perfect. All right, well, thanks again for the opportunity to talk about some of my research career. So my name is Jacob and I've been an astronomer for the past 8 years, post-studies, and this is sort of some of the things I've worked on and some of the cool experiences I've had. So this talk will have a bit of science, so if there is any questions and things during, if you have any clarifications, feel free to, I guess, put the questions in the chat or something. I might answer some of the questions, but if not, if there's anything that is confusing, hopefully we can work through it at a nice pace. So I guess to start with, I'll just talk a little bit about myself. So as I said, I've been an astronomer for the past 8 odd years. I've been very fortunate that post my studies, I've been able to work over in Europe, in the UK, and over in South America and Chile. I've been able to visit a lot of really cool telescopes. We've got in the top corner, we've got the twin telescopes of Las Campanas. This is the Magellan twin telescopes, Bard and Clay. We've got in the center, the Anglo-Australian telescope in Coonabarabran at Siding Springs Observatory. And then on the right, we have a telescope which I visited, but unfortunately, unlike the other two, I didn't get to use personally, is the ESO 3.9 meter telescope in La Silla. And so I've been able to use many of these facilities and other ones as well to investigate galaxies outside our Milky Way and trying to understand how galaxies, such as our Milky Way, sort of evolve and change over time. So post my studies at Monash University, I moved to the UK. So this is possibly the sunniest you'll ever see, the University of Birmingham. There's usually a lot more cloud cover, where I did a 2.5 year postdoctoral research position. As part of that, for teaching and for outreach, we helped use the half-meter telescope, which I've got in that picture you can see on the right-hand side. And that half-meter telescope is used for student projects and for showing the public and getting engagement with the public. It's connected to a CCD, but there is a potential way of getting an eyepiece in there so you can look at the sky on those rare days where the UK sky is actually quite clear. Following that, I moved to Chile in the port city of Valparaiso, where I worked at several universities, most notably and most recently the Universidad Técnica Federico Santa Maria, continuing my work and research in galaxy evolution. Now, as part of this, one of the telescopes I just thought I'd mention at the University of Valparaiso is this 61 centimeter telescope that they have. This is a retired telescope from ESO. So this used to be in La Silla, but has since moved to Valparaiso in sort of the middle part of the country to, again, be a teaching and outreach telescope. So it's been repurposed from what was a research telescope back in the days in La Silla. So I guess we want to talk about, what I do and what I'm interested in, and then the good place to start of this is our galaxy. So this is an artist's impression of the Milky Way galaxy using data based off the Gaia spacecraft. So this is not just like an artist, giving an impression of it, but this is sort of an artist's impression guided by the idea of data to sort of show where the stars are and what the shape of our Milky Way looks like. Now, our Milky Way is a pretty large galaxy, somewhere in the order of 200 million times the mass of our sun, depending on which estimates you use. So it's quite a large. It's got a big spiral shape, lots of stars forming in it, lots of gas. It's physically, as well as being heavy, as I said, nearly 1 trillion times the mass of the sun. It's also large, so it's about 90,000 plus or minus. Again, depends on exactly where you call the boundaries. About 90,000 years for light to travel from one edge to the other. So it's quite a physically large galaxy. And a lot of people have probably all seen this, and you probably do know a little bit about what our galaxy shape is. But what I also like to show in this one is sort of a reminder of what these shapes can look like in other ways, because what we don't often see is our galaxy side on. Now, obviously, we can't look at our galaxy side on, so this is, again, another artist's impression based on that data from the Gaia Space Telescope using the positions and motions of the stars it can see. And it shows that the galaxy, while it is quite large as a pinwheel, as that sort of spiral shape, it's not quite as thick. It's still 10,000 light years along the bulge, but it's a lot thinner. And so the galaxy sort of has, bigger in one plane and then smaller in the other one. And just a bit of a reminder on what our galaxy looks like if we look at it from another direction. And this is a little bit closer to what we sort of see in the night sky when we look up and see the Milky Way going sort of north to south. But our galaxy, as most people will probably know, is not the only one, but one of millions and billions of galaxies that we have and can observe. There are lots of galaxies that we have named and catalogued, and countless more that we've only just got identifiers for or haven't even really known about and haven't really given names to. The closest galaxies to our own, this is the galaxies that make up the local group, include the Andromeda Galaxy and the Triangulum Galaxy. So these galaxies, along with the Magellanic Clouds and M32 and the smaller dwarf satellites around the Milky Way and Andromeda, are sort of a local group. So these are gravitationally bound. So as the expansion of space and time happens, we think that these galaxies won't drift apart, but they, through the force of gravity, will sort of hold together and eventually will collide in a long enough timescale. And so there's a whole lot of different galaxies we see. So we don't just see our galaxy and the two others. As I said, there's millions and billions of galaxies. And they've all got different sort of shapes and properties and colors and things happening. And while most people will probably know sort of the basics on galaxy shapes and properties, I'm just going to quickly go through to remind people, just in case we've forgotten. And so we see, this is a photo of Stephan's quintet, which has got a nice example of different types of galaxies all at the same time. So we've got sort of on the upper left, we've got that sort of blue spirally galaxy, not unlike the Triangulum Galaxy, or a bit like a smaller version of the Milky Way. And those have got, you can see sort of that blue colors coming from new stars being formed and lots of dust lanes from gas that's being condensed and spit out by new stars forming and evolving. We have down the bottom, to contrast this, the elliptical galaxy. So this galaxy is quite smooth. It looks in the photos quite red as opposed to the blue colors of these spiral galaxies. And that's because there's a lot less gas, there's a lot less dust. And so new stars aren't being formed. It's sort of sitting there as a large ball of, or large spheroid of stars that's just sort of sitting in space and not doing not doing much in terms of making new stars and things. So with the lower gas supply, it doesn't have young stars being formed and continuously evolving. Some people call it, sort of, a bit harshly call it sort of dead, because it's not forming those new stars much. And then, of course, we have some very fun shapes. We have these two galaxies which are clearly in the midst of a merger, where the two galaxies are sort of colliding and going to crash into each other. And we think that perhaps, after these galaxies crash into each other, the gas inside them will be used up. All of that sort of extra energy from that crash is going to use up all the gas, make a whole lot of new stars, which we can see in some of this debris coming from it. And then eventually we'll use up all that gas very quickly and then end up like this elliptical at the bottom. We've also got this galaxy in the top right, which is sort of like a spiral galaxy, but is being sort of contorted by its friends and its neighbors. It's sort of got this tail of things. So it's not directly colliding with another one, but it looks like the tidal forces and the force of gravity on different parts of the galaxy are sort of pulling it apart a little bit and causing it to have a bit of an irregular shape. And those are sort of the main galaxies. We've got those blue star-forming spiral disk galaxies. We've got the red, quote-unquote red and dead elliptical galaxies with lower gas, lower dust. And then we've got those intermediate stages, such as these mergers and these galaxies that have got these tidal features or these other features of irregularities. Now, I've sort of mentioned our local group of galaxies. That's us, Andromeda, and Triangulum. And I've also mentioned this previous group that I was talking about, Stefan's Quintet. If you look in the local universe, sort of, around the last billion years or so, most of the galaxies we see are found in what's called a galaxy group. Now, that just means that, much like our local group, the galaxies, the force of gravity between them means that they are held together. The space and time is not going to pull them apart. These galaxies are going to evolve as one sort of gravitationally bound system of galaxies. Now, they'll move around each other. They might collide. They might contort each other a little bit. But that's what a group of galaxies is, as sort of implied by the name. Now, if we add more and more galaxies to a group, if we grow up bigger and bigger, much like as a village becomes a town, becomes a city, a galaxy group will eventually get enough members to be sort of called a galaxy cluster. And a galaxy cluster is sort of just a larger version of a galaxy group. More galaxies together, sort of hundreds or even thousands of galaxies, all in one place, and this is a galaxy cluster. We see lots of different galaxies. This is a picture of the Coma cluster, hopefully you can see on the screen. And you can see lots and lots of different sized galaxies and different shaped galaxies. We've got a spiral on the left, a couple of two big elliptical galaxies in the middle. And these things are huge. These are some of the largest gravitationally bound structures that we have in the universe, because these are all, most of these galaxies you see in this picture are gravitationally bound. So again, they're not going to fly off. They're not moving fast enough to sort of run away. They are held all within one sphere of sort of gravity. And this is through the combined efforts of all the galaxies with their mass and also dark matter as well, which is sort of helping hold these galaxy clusters together. Now, we observe these galaxy clusters quite easily because there's a lot of galaxies in one area, so that means it's quite easy to spot usually. And they also seem to have a lot of those, as you can see in this picture, those sort of red elliptical galaxies with not a lot of that star formation going on. Now, galaxy clusters have more than just the galaxies. As I said, there's also the dark matter. And we sort of know that because we can measure it through the X-rays. So this is the same cluster. I'm going to do a couple of blinks between them. And what we see in the second image is a purple bluey hue, and this is X-ray emission. So we're detecting diffuse X-ray emission in this galaxy cluster. Now, what happens is if you get a lot of mass, like a whole bunch of galaxies in a cluster, it will pull in the surrounding, particles, gas, dust, because it's attracted to the heavy gravity of the cluster. As this falls in, as this gets pulled and sucked in, much like anything under the influence of gravity, it speeds up, and these particles, this dust, sort of gets faster and faster as it's getting pulled towards the middle of the cluster. Now, these particles that get pulled so far and basically fall into the cluster so fast, they effectively heat up all these particles, And the sum of all these sort of dust and particles is what we call the intra-cluster medium. It's sort of a very, very, very diffuse plasma that we can see with the X-rays, and that shows us sort of where the mass of the cluster lies. So in this image here, we can see the pink is where sort of the middle of the cluster is, and then sort of the edges of the cluster sort of around the blue out towards the edges. And this gives us an idea of sort of how heavy these galaxy clusters are, because we can sort of measure the X-rays, and the amount of X-rays is sort of proportional to how much gravity must be sort of pulling in and holding in these particles and dust which give off the X-rays. And so this is another part of the galaxy cluster. So there's the galaxies, there's the dark matter, and there's also this gas and plasma, which we call the intracluster medium. Now, one thing we also know about a way to measure these galaxy clusters is through the warping of space and time. Now, you might have heard this in other talks, so I won't go into it too much, but basically with a galaxy cluster having so much mass, as light travels, it bends around a cluster and then gets reflected to us like or refracted to us, I should say, like a magnifying glass. So this cluster here, we can see these trails going around the cluster, and that's due to this cluster basically magnifying a background source and sort of distorting it a little bit. And this allows us to see galaxies that are much further back, and also we can, given we know how to understand the galaxies which are from the background, we can then use that to measure the mass of the cluster in the middle. So the cluster in the middle that's doing the magnifying, if we know how the light is bending around this cluster, we can use that to measure the mass and understand what this galaxy cluster is made of. But what I'm interested in is how galaxy clusters and how galaxies can change as they fall into these clusters. So we've seen previously that we've got galaxies like our Milky Way, like these two pictures at the bottom, that have got lots of blue, lots of gas and dust. And then we looked at those galaxy clusters, if we go back a few images, and we can see there's a lot more red galaxies, a lot more dead galaxies. So galaxy clusters must change galaxies as they go into these clusters. And that's what I'm interested in. That's what my research is sort of focused on. And then one way we can do that, as we've already spoken about, is a galaxy collision or a galaxy merger. So I've got this nice video which shows how galaxies can collide and how we can see some of the observations to sort of understand how these galaxies collide. So this is a simulation of two galaxies not unlike the Milky Way and its neighbor Andromeda. And these are some sort of images which would show different phases of how these galaxies would change and contort during a head-on collision. Now, in a space like a galaxy group or a galaxy cluster, a lot of galaxies in one small space, galaxies flying past each other or colliding is quite common. So this is a good way of sort of changing galaxies from these spirals that we saw at the start of the simulation and turning them into different forms of galaxies like we're seeing here. And we can see lots of arcs and curving debris tails as these galaxies start to collide. And a lot of these stars will actually end up sort of leaving the galaxy and being flung out into space to be sort of stars that are without a parent galaxy as well. Now I highlight here some very sort of famous ones. We've got the antenna galaxies down here in the bottom left and the lower right. We've got sort of two other galaxies that are sort of known to be colliding. But I've put over here, and I've put this as a specific one. This is a bit of a different one that we can see over here. And this is from one of the studies I was a part of. So this was a study we finished in 2023, looking at this galaxy and this galaxy, because this is a very, very, very long galaxy tail. So this debris you might be able to see in this bottom part here is all associated with the one source. So this is an image from the Dark Energy Cam, or DECAM, in Chile, and it shows this very, very, very long potential tail in this galaxy. I think the tail we estimated was about 350 kiloparsecs. So that would be about 1 million light years long, I think, as just a back of the envelope calculation, about 1 million light years in length. And this is observations that we took while I was at the Magellan 6.5 meter telescopes. So this is this source here. We called the Kite Galaxy because of the long sort of string attached to the galaxy at the end, like a kite. And I went to the Magellan telescopes in Cerro Las Campanas in the Atacama Desert in Chile, and got to use the telescopes to confirm that this object was real. So the objective of our observing wasn't actually to take the photo, but was to get spectroscopy to actually measure the emission coming from the tail to determine what the emission was and how far away was it compared to the galaxy, so we can sort of map what the tail was doing. So this is the observatory. This is the Magellan Bard, the one I used. It was very windy on the first night I was up there, so apologies for that sound. And on the inside, here is the actual telescope. So this is the 6.5 meter primary mirror, and this is the telescope on its side. We can see the primary and the secondary mirror up here. And of course, while that's really cool, you can see the size comparison. That's sort of a step that you would use to step up and look at it. I wasn't allowed to step up and get too close to the mirror, of course, because that's a very, very precious mirror. But most of the night was spent sort of at the desk taking spectroscopy of this source. And eventually we took the spectroscopy, we reduced the data, and we found this object and ended up publishing a small paper talking about that galaxy. And the interesting thing with that galaxy that we found was the source in the middle, around about here. I don't know if you can see it very well. It was actually big enough that we think that that was a third galaxy that sort of flew between the two of these and got shredded apart as it flew between the two galaxies. And that caused this long, very collimated, very linear tail. But there's another way we can cause galaxies to change in galaxy clusters. So I previously spoke about the hot gas, that intracluster medium, that very fine plasma that goes through that galaxy clusters that we can see in those X-rays. Well, when a galaxy first comes from sort of outer space or out in the cosmos into a galaxy cluster, it can actually feel the presence of that intracluster medium, and that can interact with the gas as it moves into the cluster. What happens, as this video will hopefully show, is as the galaxy moving hypothetically towards the left here, it feels the gas of the intracluster medium, and that causes the gas in the actual galaxy itself to sort of be stripped away and blown away like a wind. So this wind we call ram pressure stripping. And this is what happens as a galaxy moves from sort of on its own and into a galaxy cluster. It feels that intracluster medium and it starts to lose its gas. Now, that gas, as it's sort of being stripped, can make new stars, and those new stars can then be observed in real observations of galaxies. And so what we do is we can see jellyfish galaxies. So this is an artist's impression of how a jellyfish galaxy would form its sort of trails behind it and tails. So as the galaxy, in this case, moving sort of up and to the left, moves towards the center of a galaxy cluster, the intracluster medium will push the gas out of the galaxy and form these long tails that you can see here. And we see in actual real-life observations, we see these tails. So this is an example of a jellyfish galaxy that has a very, very long tail. We can see in the X-rays this sort of blue tail here of hot gas that's been heated up from interacting with this intracluster medium and then being stripped away in a tail. We can also see, if you look very carefully and if the resolution is good, there's these very faint blue stripes in this tail as well. And that's actually new stars being formed as the gas is being stripped from the galaxy and collapsing in on itself and forming new stars in it. So we can also see these tails for these jellyfish galaxies with radio waves. So this is using radio dishes such as the VLA or the SKA, the one being built in Australia, to look at the neutral hydrogen gas. Now, neutral hydrogen gas is sort of the fuel for making new stars. It's just hydrogen just on its own, not ionized, not heated up or anything. And as the galaxy moves into the cluster, in this case for these two galaxies, NGC 4405 and NGC 4452, the contours show this neutral gas, this fuel for star formation, being contorted and sort of pushed as these galaxies move down to the right. So this is showing that the gas is being compressed and pushed away and pushed out of the galaxies they're moving. Now, with optical telescopes and UV telescopes, such as the Hubble Space Telescope, we can see these new stars being formed. So this is a great example of a jellyfish galaxy known as JO206, a very poetic name, I guess, where we can see the galaxy moving probably up and to the left, and all this debris coming off the galaxy, not due to a neighbor or not due to the force of gravity, but due to its motion as it moves into the cluster. And as the gas is being stripped away, much like as you drop a tablet or a Barocca into a glass of water, and the gas or the part of the tablet is sort of being fizzled and creating these tails as the galaxy or the tablet moves down into the center. So there's a whole bunch of different ways we can observe these galaxies, from the X-rays, the radio waves, and with the optical and UV galaxies. So there's a lot of really amazing pictures of jellyfish galaxies. So here's a few more. Again, with the Hubble Space Telescope, we've got, this one is side on. So this is sort of a throwback to the early image of our galaxy, where we see sort of that disk galaxy side on with the gas being stripped downwards. This galaxy here is more face on. And so as the galaxy, in this case, I believe, is coming towards us, the gas is being stripped behind it in different directions. And these two galaxies here, again, another couple of edge-on galaxies, like in that edge-on galaxy of the image of the Milky Way. And the gas, and you can see the gas and the dust are both being sort of blown as the galaxies are moving in towards their parent clusters. Now, astronomy is an astrophysics for observing and trying to understand how this works. It's a very slow science. We can't wait and watch as a galaxy transforms. You know, the Milky Way and Andromeda aren't expected to merge for at least another few billion years, if I remember correctly. So getting a buildup of how galaxies evolve and change doesn't come from us watching one galaxy for a long time, but getting a whole bunch of snapshots of different galaxies and different modes of transformation. And that's what jellyfish galaxies are really, really useful, because these galaxies are in the middle of their gas being stripped away, having that transformation occur as it happens, that sort of smoking gun, if you will, of how galaxies can evolve as they fall into a cluster. So exploring and understanding these galaxies is really useful. And so this is a project that it started by a group in Italy and has expanded to include people from many different countries to understand and investigate these galaxies in as many galaxies in as many cases as possible. Now, these are some images taken by my collaborator. Unfortunately, I got to use the VLT to do some research, but during that time it was COVID, so I wasn't allowed to go up to the telescopes because they were trying to keep the people on site sort of free from any from getting sick, because these observations, you know, they're very, very useful and very, very critical to get as many as possible. So this is my friend Callum, who took a trip to the VLT, the Very Large Telescope, in the north of Chile in Cerro Paranal. And this is some of his pictures here showing the domes of the 1, 2, 3, and 4 VLT telescopes of 8 meters. This one here using the laser guide star, so it looks almost like a fancy Star Wars weapon with the 4 lasers shooting up into the sky from it, atop the mountain that you can see up here in the top right image. Now we have an image of the actual mirror. So these images, unfortunately, during operations, you can't take a photo in the telescope. So I've taken these from the European Southern Observatory, which is the people who run the VLT. And this just sort of shows the scale of this size of this thing. This is an 8-meter telescope. So the one I was using previously that I visited was a 6.5, and this one here that I used later is even bigger, with some of the world's biggest telescopes that we have in the current generation. And we use this to take spectroscopy of these jellyfish galaxies to understand a whole bunch of different processes and what's happening with these jellyfish galaxies. So a couple of results. These aren't my own, but these are just some of the ones that I think are really nice that we've seen with these galaxies. So this image here, this is a paper from a collaborator, Marco Juzelik, I can never say it very well, showing the rotation. So we've got red going sort of away from us and blue going towards us, and showing the rotation of the stars as this galaxy. This is the same galaxy here, JO204. So this is the rotation of the stars in the galaxy JO204. And then when we look at the rotation of the gas, we see that even though the gas is being stripped, so you can see here this beautiful Hubble image of the galaxy with the gas being stripped, the galaxy retains the rotation. So you can see that the red of going away from us and the blue of coming towards us still sort of happens. So as the galaxy is sort of losing that gas, as those jellyfish-like tentacles are coming up, the galaxy still retains that rotation and the gas still remembers that, which is really a fun and interesting result. Another thing we see is that if we look at the metal content, and now here when I say the metal content, I mean heavy elements, basically anything that's heavier than helium, and we'll just lump it together and call it a metal. And this was traced using the oxygen abundance, so using a filter to look at the oxygen emission. And we see that the further away the galaxies get, the gas gets from the galaxy, the more the metal content decreases. And that's kind of interesting because if the gas came from the galaxy, it should retain the same metallicity as the host galaxy did. So the fact that this result shows a very low metallicity in some of the gas means that it's possible that the gas that is being stripped is actually mixing with that plasma, that hot plasma of the cluster, and mixing together when it forms stars. So it's actually forming stars that have a different sort of chemical composition to the gas that is being stripped in the galaxy that the gas came from. This is the galaxy JW100. So you can see here the outline of it with the average metal content, with blue being less and red being more. And that's the image of it in Hubble, sort of as a comparison for what the galaxy sort of looks like. We can also measure, compared to the cluster, the position and the velocity and how fast this galaxy is traveling compared to the cluster. And what we see is when we take jellyfish galaxies compared to normal cluster galaxies. Now, the normal cluster galaxies, most of the galaxies are moving very much with the cluster, and some are moving just a little bit around the cluster. All the galaxies have their own sort of internal motions. And what we see is that the jellyfish galaxies, the ones that have this ram pressure stripping, have sort of these velocities that are 3 to 4 times the sort of average expected velocity of the cluster. So they're moving at sort of 500 to 1,000 kilometers a second through the cluster. So these galaxies are moving very, very fast. And that is really interesting, but it's also sort of expected, because if we understand how ram pressure stripping works, this is the formula here for the force of ram pressure stripping. And it depends on 2 things principally. The density, sort of how much the intracluster medium has, how dense that sort of plasma in that intracluster medium is, and also the relative velocity. How fast is the galaxy trying to punch through that hot plasma? And the faster it's going, the more that ram pressure force should work. So we should expect to see these galaxies moving very, very fast, smashing through the cluster very quickly. Now, the thing about jellyfish galaxies is, despite there being lots of galaxy clusters and lots of galaxies, we don't know that many jellyfish galaxies. Part of my job in Chile was to sort of tally up and collate as many jellyfish galaxies as we know, and the answer was about 1,000. So not a big number, but yeah, about 1,000 known galaxies that have these sort of tails that we're pretty sure come from ram pressure stripping. So what we want to do, though, is we want to sort of get, as I said, more snapshots to sort of understand this process of ram pressure stripping, to better understand some of these results that I was speaking about before with more galaxies. So AI is something that could be useful for doing this. The problem with AI, however, is it's only as good as the training set you give it. You need to train AI using galaxies to then get the new ones. And as we only have about 1,000, it's not quite enough to be able to reliably train an AI to find new ones. So part of my job was to have a citizen science project where volunteers, many of you potentially have contributed to citizen science projects like this before, and to look for signs and signatures of round pressure stripping. Now, these 3 galaxies I have shown here, these were sent in by members of the public to me and my team, and they were like, we think this is a round pressure stripped galaxy, what do you think? None of these 3 galaxies have been published as a round pressure stripping galaxy. No one has studied these, and that just shows how many there could be out there that people have yet to find. And so part of my job was to use citizen scientists to help find more, and so we can study more of them. So these 3 galaxies here you're looking at are sort of round pressure stripped or probable jellyfish galaxies that no one has yet studied, which is really kind of cool. Now, I've been fortunate enough, as I said, this is a bit of a screenshot of my computer screen from earlier, and this shows me cataloging as many round pressure stripped galaxies as possible. Now, when I was first speaking to people at the ASV, I thought most of these galaxies would be a little bit difficult for me to find, it'd be a little bit difficult for people to find and observe these for themselves. A lot of them have sort of quite faint magnitudes, and these features may not be that possible. However, after attending VASTROC this year and seeing some of the incredible telescope setups and incredible sort of images that a lot of the ASV members can do, I've sort of decided to put a little bit of a list of some candidates that maybe if you have the equipment, you can try and look at home. Now, I don't guarantee these galaxies will look as good as the images that are coming from here, because these are from, I think these are coming from quite large telescopes. We've got, you know, a 4-meter telescope for a lot of these ones. So if you can't quite get these images, I do apologize, but these are some targets that I've gone through and I've seen that have sort of a southern declination, or at least an equatorial declination, and an apparent magnitude that is reasonable for some people to maybe try. And so if anyone is interested in having a go and trying and imaging these, I've put them in order. So we've got NGC 4654, Messier 99, you can see the debris going that away. NGC 3312 in the Hydra cluster, that's this one here. ESO 137-001 in the cluster Abel 3627. This one was really hard to get an optical image for, so if anyone can magnitude this, it's at about a magnitude of 13 to 14, so it probably is pushing it pretty difficult. So I'm not gonna, I don't know if anyone can get that deep, but if you can, I can't find a good optical image of this galaxy, so I'd love to see one. And then finally, for those who seem to have the crisp, best, darkest skies and biggest scopes, then we've got this one here, SDSSJ, blah, 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 which is a magnitude 15, but that's got some really nice sort of debris flying off it. You can see a lot of the galaxy being contorted by round pressure stripping. Now, I have other suggestions. These are just some of my sort of top 5 ones that I think, between the declination, the brightness, and how jellyfishy they look, are some good ones that potentially, if anyone's interested, might be a fun little challenge for someone. And the future for this, well, as many people know, we have some very massive surveys coming up, which will really help us to find new jellyfish galaxies and understand how galaxies can transform as they sort of enter a galaxy cluster. So we've got the images of, on the top is the Vera Rubin Observatory, which is a very, very large optical observatory, which is going to basically image the southern sky, the whole sky, sort of once every week or so, and then just keep going deeper and deeper to get all those faint pictures. And the bottom, a lot of people have probably heard about the Square Kilometre Array, the SKA, which is going to map those radio waves, looking at that neutral hydrogen gas, that fuel for star formation, to try and find new jellyfish galaxies with that radio gas. So with that, I'll leave you with this beautiful image, another cluster that someone found from the public and said, I saw this in a press release about lenses, look at these beautiful jellyfish galaxies. So with that, I'll leave it to you and say thank you.
Better unmute myself, sorry. A wonderful We'll talk. We do have a question. You kind of answered this question from Andy, but I think we can look at it from an angle of, you said there's 1,000 that are known, but I guess from Andy's question is, how rare are jellyfish galaxies in the universe? Or are most galaxies in the middle of their rotations to becoming jellyfish galaxies again later on? So I guess, you said there's 1,000 that we know of, which means at the moment, from our point of view, they would be considered rare. But are they rare? Or is it just we just haven't seen that many of them yet?
Yeah, so there's a combination of a couple of things, which means the answer is yes and no in terms of how rare they are. Now, as I said, a lot of these things we just haven't looked at. The jellyfish galaxies sort of have their own unique shapes, so AI hasn't found them and automated methods haven't found them, en masse. So we're sort of relying on people to go galaxy by galaxy going, yes, that is, no, that isn't, yes, that is, no, that isn't. Now,
could it be that, like you're saying, so it's a fairly new, I guess, field, that there's a lot of people who may have seen some that may not have been catalogued but don't know that that's what they are?
Yeah, definitely. In the few clusters we have done, like we've gone through galaxy by galaxy, yes, 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 no, yes, no, 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 whatever, we see that they happen to be about somewhere between 1 to 5% of the galaxies. So we're talking 1 in 100 to 1 in sort of 2025 of these galaxies are likely to have some tails and some debris, which would be consistent with ram pressure stripping or them being jellyfish-like. So we think they should be, if there's 1,000 galaxies in every cluster, or which is not all clusters, that's a big cluster, but if there's 500 to 1,000 galaxies in every cluster, then we're expecting sort of 5 to 10 jellyfish galaxies per cluster. Now, we haven't got that many because we know of many more clusters than that, but they will be there. So the answer is they're rare enough in terms of they're about 1% to about 5%, but that number is probably a lower estimate because we've only looked at a few clusters to find them. Yeah.
We have another question from Ronald. When you do spectroscopy on those long tails, can you assess Doppler shifts and see how fast different components are moving? So I guess he's talking about the different parts of each galaxy. So when the different metals and whatnot.
Well, this is sort of what this figure is showing, this bottom panel here. I'm just letting it, I don't know if it's slower, but in this figure, we're seeing sort of that Doppler shift. So this green is sort of not moving with a velocity relative to the central velocity. And then this is sort of the rotation here. We're seeing that Doppler shift in emission lines. So this is using that Doppler shift to see that jellyfish gas rotating and things. And that's how we can build up those maps of these galaxies. So yes, we definitely use Doppler shift, and that's what this is sort of doing. That's that relative velocity, changing those emission lines through the Doppler shift to get the rotation, and how we found out about this.
Wonderful. And we don't have any other questions that I can see, unless we'll bring Bill in, unless Bill's got a question he would like to ask you, having now finally seen your presentation because he didn't get to see it at Vastro.
Hello.
Hey. Do you have a question, Bill, or you've got no questions?
I don't actually have any questions. I've just been sitting here looking at the awesome photographs and figuring out if this rotational the rotation in the stripped off gas that continues. Is that? I mean, I can only think about this within Newtonian terms, because it's like with my Newtonian hat on, I couldn't. That would be what you'd expect, wouldn't it?
So the question, I guess, was, as the gas is stripped out, does it sort of mix straight away, and how long does it retain? Does that remember it? Because yes, the inertia and momentum, it should stay out. But the question is how, like, the gas as it's being stripped, how sort of not gentle, but like how is it being stripped very linearly? Is it doing that? And so that was the interesting part, was if the gas, as it's being hit by that intracluster medium, is it sort of being mixed and it's very turbulent, but obviously it's retaining that rotation well enough. And so that was the sort of interest about it, is it's not being mixed up in a sort of turbulent environment.
Okay, fair enough. I've got a follow-up question. You said that the metallicity of the stripped off gas changes as it gets left behind. How is that happen? Is that because of star formation or something?
So there's a few different theories. So this is something that was published, I think, about 5 years ago, or maybe it was a bit less. Let's see, 2021, so 4 years ago. And what they saw was, here we can see this galaxy. This is JW100, and so this is the average oxygen abundance, which we're using as a proxy for your metal content. And as it goes further away, the gas becomes less metal rich. Now, part of that may be due to the fact that in a galaxy, if take the Milky Way or whatever, the gas on the very outside is less metal rich than the gas in the very middle. So if you remove first the gas on the outside, that will be the stuff that's stripped first. Then that will be the lowest metallicity. But they think, the authors of this study, I wasn't a part of this one, that the gas is actually mixing with the plasma of that intracluster medium, and that plasma has a low metallicity, and so that's basically making the result lower because it's mixing together. So it's causing a change in that. Yeah, it's basically diluting it as it's being stripped away. Okay. So it could be a combination of the two. They can't rule out the idea that a lot of it is just the outer gas, which will have inherently lower metallicity, but it seems to be too low for what we know of the gradient of metallicity in most galaxies. So again, it's one of those snapshot things. We can't look at the gas before and after, so we have to sort of infer.
Yeah, I was about to say that there's only one way of finding out, and that's waiting.
Yeah,
but
exactly.
That's probably not really an option.
Not really an option for me, at least.
You could wait, Bill. You're used to waiting, aren't you? To Corona Borealis, still waiting.
God, yeah, I'm still waiting.
Still waiting. Well, Jacob, that was an absolutely wonderful presentation. Bill, I'm glad you got to see it, and Jacob, I'm glad you've extended it from what I previously saw as well. It's very detailed. Everyone's loved it, that's for sure. And we thank you for coming along tonight to give us a talk on Jellyfish Galaxies.
Oh, you're very welcome. Thank you guys for the opportunity. It's great to share some of my passion and enjoyment and the research that I've done. So, and if anyone if anyone can actually image some of those jellyfish galaxies, I would love to see them, because, as I said, until a month ago, I thought it would not be possible for without some of the biggest telescopes. But I've seen some of the images that the ASV can do, and it might be up to the challenge.
Can you, if you could email me through that list? What I'll do is I'll share that with the members, and that way we can see what they can come up with for you.
Excellent.
We'll get them to start with the difficult ones first.
See what they can get. All right,
yeah. Wonderful. Thank you very much, Jacob. Bill, it is time for you to share your screen and share with the viewers what's in the sky for late September and early October. Do we need some elevator music while we wait, or
have I? Can you see it there?
Yes, straight up. How's that?
Oh, I'm getting good at this.
Getting good at this. You've done this long enough now that you're getting good at it. I think
this is my 19th one.
19.
Something like that.
Only 19,000 more to go, Bill. All right. I'll remove Jacob and I from the stream,
right,
and we'll let you get stuck into it.
Okay. All right. Well, this is the what's in the sky for late September and early October. Let's see. Let's see if I can get rid of that. Just push that up there. Right. Okay. Tonight, as usual, this presentation is being held on the lands of the Bunurong and the Wurundjeri peoples of the Kulin Nation, and I wish to acknowledge them as traditional owners. I would like to also pay my respects to their elders, past and present, and Aboriginal elders of other communities who may be here today. Okay, so I'm going to talk about general conditions at this time of year. This is the usual part of this talk. Then I'll get into the what's in the sky, starting with the moon, the planets, and then I'll talk about getting orientated. Then I'll suggest some targets for tonight and talk about what the sky is going to look like tomorrow morning. And finally, I'll end up with things to look out for this month. Okay, general conditions at this time of year. we're starting to get towards the spring equinox. It's already brighter. You can see that the sun is starting to move increasingly quickly. Obviously, at the equinox, that's when the time of the daily change is maximized. 21st of September, which is in 2 weeks, something like that. That's the astronomical end of winter. It's actually, I think it's 22nd or maybe even the 23rd this year. We're getting late in the leap year cycle. The average minimum temperatures are starting to rise, which is good news for people who hang around the LMDSS all night. And however, cloud-free nights won't get better for a few months. There's a bit of a lag there. That the data on cloud-free nights is not as bad as it actually looks in the statistics, because remember, cloud-free nights is 1 minus the completely clouded out nights. So cloud-free nights includes partly clouded nights. Now, sunset tonight was at 5:43. It's dark about 27, and sunrise tomorrow is at just after 7 o'clock. It's dark until about 6:15. Now, whoops, I thought I had an extra little bit there. So I was about to say this was civil darkness I talk about, not astronomical, which is a bit shorter. Okay, for you cheese lovers out there, the moon over the next few weeks. The last quarter is on Sunday the 14th, so that's coming up fairly shortly. It's on the 14th, it's about as far north as it goes, so it's going to be very low in the sky. It rises at midnight, sets at noon, and then over the following week it will be a waning crescent, as it always is at this time of year, this time of week, month. It'll get thinner and more difficult to see as it gets closer to the sun. Those really thin crescents are hard to see. And you'll view it in the morning and later the week of the 14th in the early afternoon, just before sunrise. The new moon is on Monday the 22nd, which means that LMDSS is the weekend before that. There's a partial solar eclipse, but only if you happen to be in New Zealand. Now, the moon has just crossed to the south, so in a couple of days the crescent will be setting in the southwest. You'll be able to see it in a few days as a waxing crescent. You'll have to look after sunset, which is rather pretty if you look west. First quarter is on the 30th of September. It's Tuesday, so a little bit more than a week. It rises at noon and sets at midnight, which is for the cheese lovers. It's the best viewing time. In the following week, it'll be waxing gibbous. It'll be deep in the south, which means it'll be very high in the sky. So this is the prime time for cheese lovers. Full moon is on the Tuesday the 7th of October, and it crosses back to the north on the 12th, so that means after that it's going to start to get lower again in the sky. The full moon is close to its minimum distance, so it's going to be a supermoon, so expect the media to lose their nuts. And over the following week, it's going to be setting in the early morning as waning gibbous. Now, I know I've shown this graph on several occasions. I'm going to show it again because it's eclipse time of year. The full moon, that's when the green line is the proportion illuminated, so 100% is a full moon. Full moon is on roughly the 8th of September, so that's last week. And the declination of the sun is just over 5 degrees, and the declination of the moon at that time is just under 5 degrees, which means that there's a lunar eclipse, and that's the one we saw the other night. The new moon, which is when it's zero illuminated, is on the 22nd or thereabouts, and at that point, the declination of the sun and the moon are the same, and that indicates that it's a solar eclipse. So there you go. There's that Dan graph again. Okay, this is the younger astronomers part. Now this one's a little bit ambitious and might get a bit complicated. There was a lunar eclipse a couple of days ago, which you'll probably see. That's my slightly okay picture there. There's going to be a partial solar eclipse 2 weeks later. Now, why is that 2 weeks? So you see if you can figure that one out. The hint is that it takes the Earth a whole year to go around the sun, but only takes a month weeks for the moon to go around the Earth. So how do the positions of those three bodies change in that time? So, and for extra credit, see if you can make a diagram of the solar eclipse and the lunar eclipse showing where the sunlight comes from. You don't need to actually draw the sun, just a piece of paper. You'll be too big because it's going to be a long way away. You need to draw the day and night parts of the Earth. That's the light and the dark bits. The orbit of the moon around the Earth, where the moon is during a solar eclipse and where it is during a lunar eclipse. And see if you can figure all that out. You'll be ahead of the pack. If you can draw the Earth's equator over your diagram, you probably draw it, and most people draw it so the light comes in from right above the equator, but you don't have to, and that's fine because it doesn't always come from this angle. The spring equinox is coming up, which is where the sun does actually go over the equator. But where does the sun's light come from in summer and in winter? It's a different diagram. That'll keep you busy. Okay, planets this month. Mercury rises about 6:30 in the morning and it sets before sunset, so it's very much in the sun's glare. Venus, 5:15 rises and it sets before sunset. It's still good morning viewing. It's getting closer to the sun though. It's also getting less bright. Mars sets about 10 minutes to 9. It's moving terribly slowly, as Mars does, and it's very low. From Melbourne Observatory, it's always behind either a building or a tree. I think Mark gets a better view of it from the Mercer, but down on the ground where I'm staying with the trout and Sims, yeah, definitely behind a building. Jupiter rises at about 20 to 4 in the morning, and it's a really good morning object. I can see it from my backyard in the mornings. Saturn, this is the best all-night object. It rises just before 7 p.m. and it's in a really good viewing position around about 9 p.m. As long as you're not too close to the trees. So you can watch that all night, just about. And its rings are still very flat. They'll be opening up over the next 7 years or so. But yeah, they're very pointy at the moment. Uranus rises just after midnight. It's between the Pleiades and the Hyades, which means that you're going to have to stay up fairly late. It should be findable with patience. I would use a Schmidt-Cassegrain telescope. It's going to need you're going to need a lot of focal length to spot Uranus. Yes, it's you can tell the difference between Uranus and a star because Uranus is sort of a bluey-green color. Neptune rises at 7 p.m. It's actually very close to Saturn. Unfortunately, we nearly got a shot of it, or nearly got a view of it through the Troughton and Sims just the other night, but we were dodging the clouds, and I couldn't actually swing the telescope to get it in time, unfortunately. Pluto, which is a planet, sets at quarter to 5 in the morning, and it's still worth a shot. And by a shot, I mean a photographic shot. You're going to need to take a photograph and then take another photograph a couple of days later and spot the difference. Okay. Time to get orientated. This is the sky, 10 p.m. facing south. So we always look for the 3 major signpost constellations. But first, our little wheel. Somebody was asking me the other day. I put this clock face up there, and she wasn't quite sure where it goes. Grab a ruler, a 40 centimeter ruler. It's about 38 centimeters from the horizon. If you hold the ruler out at arm's length, he said, making arm gestures. I don't know why, I've got no camera. So that's where it is, and it's obviously due true south. So let's get rid of that. Okay, so the major signpost constellations. The Southern Cross is at 4 o'clock on that dial, and as you can tell, it's getting fairly low in the southwest. Rigel Centaurus, the double star Alpha Centauri, it's still worth a good look, but I'll probably be moving away from that in the next month or two. There it is. Scorpius, which is that backwards question mark, it's now past the meridian. It's sort of starting to get towards setting. It's about 45 degrees, but it's a very large constellation, so it sort of spans a lot of degrees there. Anyway, you can spot it. Orion, on the other hand, you can't see. It's up during the day, and it will be up tomorrow morning. It tends to rise at sort of 3 o'clock-ish in the mornings at the moment. So major stars, we've got Canopus, which leads the cross around the celestial pole, which is currently very low in the south-southeast. It's probably behind trees from where you are, where most people are, unless you're up a building or something. Achernar, on the other hand, is getting higher, and that's opposite the cross, but it's further around from Canopus. So let's get rid of that. There we go. Fomalhaut is approaching what we call the donut hole. It's sort of getting towards the zenith. It's quite in a quite good viewable position at the moment, but you need to give it a rest in the middle of the day or in the middle of the night, because it's getting too close to that zenith, which is hard to hit. Antares, it's getting lowish in the west, in the middle of Scorpius there. Nice reddy yellow color. Okay, there are two stars in the northwest. The one in very low is Vega. It's probably going to be very hard for you to see. It's behind most different it's even beyond blades of grass. It's very low. Higher in the sky is Altair. Altair is quite good for the moment at the moment, and I use it for looking for Albireo. It's a good little signpost for that. Saturn is the only planet which is up at the moment. Well, the only obvious planet that's up at the moment. It's getting into a nice viewable position. It's now in the east. You can ignore the moon because it moves around all over the place. Okay. Now let's have a look at some visual targets for the evening this month. I've got a nice little list for you. Some of these are the same as the Vastrock talk, and some of them aren't. So okay, so start with Alpha Centauri, nice little double. It's still quite available. M7, that's Ptolemy's cluster. That's just off the coast of the Scorpius. There's M6, the butterfly cluster. That's, I think, a prettier cluster than M7, but you may be the judge. 6231, NGC 6231, the False Comet Nebula, the name of which I absolutely love. It's right in the corner of Scorpius there. The other end of Scorpius, Beta Scorpii, that's a double. It's not quite as wide as Alpha Centauri, but it's a very pretty little double. 6281, Mothwing Cluster. I have marked that as a donut, but only if you're up fairly early in the evening. It's well past it by 10 p.m. That's an interesting one. The Wild Duck Cluster is a blob, I think, and it's something which I haven't actually spent a lot of time on myself, but it's probably worth a look. Beta Cygni is Albireo. I mentioned that before. Very pretty. It's one of my favourites, and the people at the observatory love seeing that. If you've got a pair of binoculars, something with a large, wide field, the Brockie's cluster is a lot of fun. It really does look like a coat hanger, but it's very big. You can't see it in a telescope. You need a 7x50 pair of binoculars. 47 Tuc is coming into view. It's starting to get quite high now, along with the small Magellanic Cloud. Particularly from a dark sky site, it's really good. In fact, 47 Tuc you can see with your naked eye in from LMDSS or a dark sky site. Saturn, obviously, a little bit later in the evening when it rises higher, you want Saturn to be as high as possible, so you're looking through as little atmosphere as possible. Okay, that's visual targets for this month. Photographic targets, these I have brazenly stolen from ASV members over the last couple of months. So again, 10 p.m. facing south. Rho Ophiuchus. This is Simon Walters has just got back into astrophotography, and he started with that. Look at that. Isn't that beautiful? That's a great shot. M20 from Ross Horton. M20 is very popular at the moment, but it's starting to get past its prime area in the evening. You won't be able to get a lot of hours on that. The Prom Nebula, again, thank you, Jessica, is again past its prime a little bit, so you probably want to be looking at stuff on the east at the moment. I'll try to get back to that. There's the M6, as I said, beautiful little cluster. You can actually see the butterfly shape if you use a bit of averted imagination. Eagle Nebula, the M16 from Andy. That's on the other, on what I think is the other side of Scorpius. I normally think of the close side as being the cross side. Omega Nebula from Gerald. That's another nice shot. Western Veil, it's a very difficult thing to get because it's low in the sky. You're probably looking through a lot of atmosphere. Kelly's done a wonderful job on that. It's the Western Veil is also known as a witch's broom. It does actually remind me a little bit of a Nimbus 1000, or what it was called. Helix Nebula is just starting to come into its season now. It's you get it at 10 p.m. You'll be able, as long as you've got a meridian flip under control, you'll be able to get quite a lot of hours on that. So that'll look quite nice. That's a shot from last year, I think, from Anne Marie. 6744. I didn't even know this one existed until I hit it with the South Dome. It's just past the meridian, so it's in a reasonable position still. It was just a test image. NGC 300. It's one of Jeff's. I don't remember when he got that, but that's also coming into its prime time about now. You can see this is, by the way, this is one of those the star forming galaxies. Lots of blue nebulas and stuff like that. Another one from Jeff. This is a planetary nebula, IC 5148. Planetaries are very, very small, so have a go at it if you've got a long focal length. I don't know what Jeff was using. It might have been that AstroWorks telescope. 1532. I love the shape of this thing. It's really, really cool. It's very, very low to the ground at the moment. It's probably still a little bit early for it now, but that's a weird shaped galaxy. So might be one of your candidates. I'm not quite sure. Small Magellanic Cloud. It's not something I normally bring into these things, but Kelly's done a marvelous job on that. I don't know what filters she's used, but that looks just awesome. And obviously there's Saturn. There's always Saturn. So that's a shot from Con. All right. So that's the photographic stuff. 5 o'clock in the morning, facing south as usual with my clock face. Southern Cross is past the lower meridian now. It's coming back up again. It's probably not in a viewable position yet. Scorpius is gone. I will see you again next year. And Orion, it's approaching a meridian. So if you want to get up and have some after midnight viewing, Orion is starting to getting quite a good position. A friend of mine sent me a sea star photograph of from England actually. He got a horse head just the other night. So yeah, it's starting to happen. For planets, we've got a bit of a streak. There's Saturn. Right next to Saturn is Neptune. Doesn't show up on the picture here, but yeah, Neptune is very close to Saturn. Uranus is just on the meridian there, and Jupiter is starting to climb off the horizon. So that's pretty much all there is. Oh, sorry, Venus not up yet. It rises at 5:15, and it's getting close to the sun. So it's kind of actually on its way out. Okay, so some random observations. What's coming up? This weekend is an LMDSS working bee if you can. I will probably be up there. The weekend after is the Galactic Center Star Party. I'll probably be there as well. In fact, I think I have to be there. That's at LMDSS as well. 21st of September, that's the day after. Saturn's at opposition, so hopefully at the Galactic Center Star Party, we'll be able to get a good view of Saturn. The couple of days later is the spring equinox. You won't actually tell the difference, but there it is. Neptune opposition, because Neptune and Saturn are very close together, so their oppositions are very, very close together as well. And daylight savings begins on the 5th of October, so that means you're going to be losing a night's sleep or something. I'm not quite sure. Daylight savings always befuddles me. It just means I'm tired. And that's it. So, by the way, if anybody's seen a yearbook, an ASV yearbook with Bill Stent written on it in big letters, can you please let me know? I use it all the time and I've lost it. I feel naked without it. So there you go.
Hey, Bill.
Yeah.
We have a member who's curious to know if you have a T Corona Borealis update.
Well, the update is that there is no update. and it's getting a little bit late in the year. For me to get a shot of T Corona Borealis, I have to get very, very early in the evening, and then it's past the meridian, and it's approaching the trees at the bottom of the astrophotographic field. So I'm a little bit afraid that I'm gonna lose it for another year, which I just don't. I don't know what to do.
You need a telescope at a high location. That's what you need.
Yes, that's what we need.
Yeah, absolutely. Bill,
Jeeves,
thank you
take me to the
again.
Atacama Desert.
Yeah, Atacama Desert. There you go. Jacob, can you take Bill to one of your fancy telescopes in a nice high location so he can deal with T Corona Borealis for the members? Yeah,
Say
there we
yes.
go. Yeah, he's saying yes. There we go. See what we can do.
Sorry, the microphone just did a funny thing there. Hopefully, we'll see how we go.
There you go.
Well, if anybody can get a shot of T Corona Borealis, because I think I've just about lost the opportunity. From the domes that I can control. So if anybody can get one, I'd appreciate it.
Okay.
There we go. We'll set a target, Bill. We'll put a memo out to everybody to try and get a photo for you, some updates.
Awesome.
Bill, thank you very much for your What's in the Sky for this month. It was very, very detailed again. I had a message from Kelly. I think she was a bit embarrassed about all the photos of hers you shared. So,
they're good. They're good
they
photographs.
are very, very good, aren't they? She's a very good astrophotographer, that's for
I
sure.
take photographs from people who are good, but I also take photographs who for targets which are difficult.
And you take photographs of people who are bad at photos too, because I've seen some of mine come up. So, anyway, thank you, Bill. Again,
I'm just being patronising.
You are, yes. And again, Jacob, thank you very, very much. It was a wonderful presentation. And next month we have Eileen O'Healy, who's going to be talking about 50 ways to die in space. Jacob's eyes lit up then because I think he remembers that one. We're going to talk.
Awesome.
It was awesome, which is why I've asked her to come and give a talk for the rest of the ASV, because I reckon everybody, and the public as well, I reckon everybody's going to want to know how you can get impaled by a snowball on Saturn. That was my favourite, that one. So we're going to hear from Eileen O'Healy on 50 ways to die in space next month. So it will be a live stream again because I'll be continuing to work from Starview Farm up here. Only about another 10 years of work to go up here, Bill, I think, maybe. No, I think we'll be done. We'll have all the work up here finished. As I'm sitting in one of the completed observatories now, we've got 5 completed observatories up here. We've got 5 more to build. We should have it all fully commissioned by November, I believe, was our target, which is great. And for those members who are watching, there will be some videos uploaded this weekend of Bill teaching you all how to use the remote observatories at LNDSS, the ones that he's been using to get the images of T Corona Borealis.
Or not.
Or not, yeah. No, the videos will be uploaded, but they are the telescopes you've been using, but you won't be able to use them to get those images anymore, Bill. They will be for the members to use now. So
I know.
Sorry?
I'm being booted. That's good.
You are being booted, yes. Members take precedence over you, Bill. Sorry, the other members take precedence over you, Bill. Yeah, don't forget, as Bill said, we've got the Galactic Center Star Party not this coming weekend, next weekend. We have a working bee at the LNDSS this coming weekend. And then grand final weekend, we have the Sea Lake Astrofest as well. ASV website has all of the information for the public events, and in the members area, it has the information for the members only events. We'll see you guys next month at the AstroTalk. Thanks for coming along.